A centrifugal pump is designed to work at a certain flow rate or head. These fixed values of flow rate and head normally lies at a maximum or optimum efficiency of a centrifugal pump. But this is not always the case. There is a chance where a pump has to be operated at a reduced flow or at an increased flow. For example, when we have a blockage or something causing the pipeline to damage, for example, then we have to operate the pump at a reduced flow, for example. So in this graph, we have three different velocity triangle of a centrifugal pump at the outlet of the pump. So in the middle, we have the design flow, and the velocity triangle represent the velocity triangle at the outlet. And then on the right side, we have the increased flow when the pump being operated at an increased flow. And on the left side is when the pump is being operated at a reduced flow. So these three triangles, we have to compare the value of Cx2 or the axial component of the absolute velocity at the outlet we need to remember that a pump is connected to an electric motor that causing the rotations or causing the omega. Since the output of this electric motor is constant, omega is perpendicular to u or the blade speed. Since omega is constant, it means that u of the pump or the blade speed is also constant. So that when we have q reduced, that means that we will have a higher Cx2. On the opposite, when Q is increased, we will have less Cx2 at the outlet. On the other hand, we can also see that the radial component or the tangential component of the absolute velocity is also increasing when the flow rate is being increased. And on the opposite way, when the flow rate is being reduced, the CR2 is also decreased. Now let's continue and see the effect of outlet blade angle to a centrifugal pump. As we know, centrifugal pump can be grouped according to the geometry of the blade impeller. It can be forward facing, radial, or backward facing. So it can be forward facing when the blade angle at the outlet is higher than 90 degrees, and it will be radial when the blade angle at the outlet is 90 degrees, and it can be backward facing when the blade angle or beta 2 at the outlet is smaller than 90 degrees. Now let's look at the case of the backward facing blade geometry of a centrifugal pump. We know that the Euler equations for a centrifugal pump, assuming there is no whirl at the inlet, that E is equal to U2 multiplied with Cx2 divided by gravity. And now according to this velocity triangle, we can define Cx2 as Cx2 is equal to U2 minus CR2 multiplied with cotangent of beta 2 at the outlet. Now let's combine these two equations, and we have energy is equal to U2 multiplied with U2 minus CR2 u2 multiply with cotangent of beta 2 divided by gravity, we will have u2 to the power of 2 divided by gravity minus, we can elaborate more on CR2, that CR2 is a function of Q or flow rate multiply with the blade speed at the outlet or U2 divided by the area of the blade. And now we will replace this with this so that we have Q multiply with U2 multiply with cotangent of beta 2 divided by gravity multiplied to the blade area. So this is the energy equations for the backward facing case. Or we can simplify this equation as, let's rearrange it first. u2 to the power of 2 divided by gravity minus u2 multiply with cotangent of beta 2 divided by gravity and area of the blade multiply with Q, and we can make a simple form of these equations as A minus B multiplied with flow rate, or A minus BQ. And this is for the backward facing blade configuration. As we've seen that when the arrangements of the blade is forward facing, we know that the equations will be like this. And now let's assume that we have a radial blade configurations where beta 2 or blade angle is equal to 90 degrees. As we know, the cotangent of beta 2 when the angle is 90 degrees is equal to 0. Therefore, for radial blade configuration, the equations will become E equal to A, or simply u2 to the power of 2 divided by gravity. And for the case of forward facing, we can simply write down the equations as E equal to A plus BQ, and it's being represented in the graph here as a function of head against flow rate, where normally E is also written as head, in form of head. And on the bottom right side of the screen, we can see the power and head against flow rate for each arrangements of the blade, either forward facing, radial, or backward facing. The red line represents the head and the green line represents the power.